Hey guys, this is Professor Janacek. I'm going to go over the calculus of vector-valued functions. So let's start with a vector-valued function. Again, that's a vector that's defined by function. So each of its component is a function. Here we have r of t, a vector, defined by the functions f of t, g of t, and h of t for its components. So let's first see if we can determine limit, and then we'll talk about continuity. So the limit of this is exactly what you would expect it to be. The limit, as let's let t approach some number a of our vector valued function r of t, well, we'll simply take the limit as t approaches a of each of the functions. Notice these are not vectors here, these are the components. We'll simply take the limit of each function, of each component function. So nothing too crazy there. That's it. There you go, taking limits of vector valued functions. Now what about continuity? How do we determine if a vector valued function is continuous? Well, it is continuous if, just like continuity for regular functions, if you can take the limit, in this case I'll let t approach a of our vector valued function, if the limit of the function is equal to that vector valued function evaluated at a. Remember that there are a couple things you need to verify before doing this. You have to make sure that the vector valued function does exist at a, and then you also need to make sure that the limit, as you approach that value, as you approach a, if that limit has to exist as well, and then of course those two values have to be equal. So there's continuity, pretty straightforward. Let's take a look at finding derivatives. Now to begin with, our functions, the component functions, have to be differentiable. So f, g, and h are all differentiable. And then, just as you might expect, to find the derivative of this vector valued function r, to find its derivative, r prime, is simply the derivative of each of its component functions. Again, pretty straightforward as long as everything is differentiable. And please note that this only works as long as that derivative is not equal to the zero vector. Zero vectors get a little tricky. There's some unknowns there. But otherwise, there you go. Pretty straightforward. I do want to mention that all of the derivative rules apply as you would expect. I want to mention though the product rule. So if I have the derivative of some function, I'll just call it f, times a vector, I'll call it, let me just call it, what's going on here? Let's call that vector u. So notice I have a function times a vector, f times u. That is, if you remember the product rule, that is f prime times u plus f times u prime. Notice though, again, f is a function, u is a vector valued function. Now what if I have two vector valued functions? I've got vector u and vector v. Remember, there are two ways of taking the product. There's the dot product and there's the cross product. However, the product rule works exactly as you would expect it to. I'll take u prime times v plus u times v prime. Again, notice all of these are vectors now. Oh, and wait. These are all dot products in here. Let me rewrite that one so it's clearer. U dot v prime. And with the cross product, as you would expect, we'll take u prime crossed with v plus, make sure that's clear, plus u crossed with v prime. Again, nothing too unusual there, but if you hadn't seen it, you might not know exactly what to expect. But there you go. Pretty straightforward, I hope. Now let's talk about integrals. If we want to integrate r of t dt, again, as you would expect, this isn't too earth-shattering, I don't think. The mathematics behind it, the proof of this, fairly straightforward even. But this is the integral of f of t dt. For the first component, we'll integrate g of t dt for the second component, and then integrate h of t dt for the third component. Right? Again, pretty straightforward. I do want to make one comment about this, that this is often written as FGH. Notice these are uppercase FGH plus the vectors C1, C2, C3. And this is for F, G, and H antiderivatives of lowercase f, g, and h, respectively. All right, so sometimes you'll see it written as the function vectors plus the constants on occasion. All right, what about the definite integral? Well, again, it's exactly what you would expect. We'll integrate over that interval for each of our functions. And there you go. Notice we always end up with these vectors. Each one of these guys ends up being a vector. The limit is a vector. The derivative is a vector. The integral is a vector. But again, nothing too earth-shattering, I hope, but quite useful. Enjoy!